In this video, we're going to be talking about trigonometric substitution. The motivation behind this section is, if we want to find the area of a circle or ellipse, we have an integral of the form, the integral of the square root of a squared minus x squared dx, where a is some positive constant. Regular u substitution will not work here. Observe, if we let u equal a squared minus x squared, if we take the derivative, we get du equals negative 2x dx, and what ends up happening is we have this extra factor of x that doesn't appear in our original integral. So the solution is that we parametrize. We change x to a function of theta by letting x equal a sine of theta. So if we do that, then our original integrand becomes the square root of a squared minus x squared gets changed into a times sine of theta squared. And then I'm going to go ahead and square that. So we get a squared minus a squared sine squared theta. Now, because both of the terms underneath the square root have an a squared, I can factor that out, and I get 1 minus sine squared theta. And then, using the Pythagorean identity, 1 minus sine squared theta is equivalent to cosine squared theta. So this is equal to the square root of a squared times cosine squared theta. And because underneath the square root we are multiplying, because of radical properties, I can break this up into the square root of a squared times the square root of cosine squared theta. And then finally, when we take the square root of both of these things, we get that our answer is a times the absolute value of cosine of theta. Generally, we use an injective or one-to-one function, so it has an inverse, to simplify calculations. Above, we ensure that a sine of theta is invertible or has an inverse function by restricting the domain to negative pi over 2 to pi over 2. So let's look at this table, which gives us a summary of when to use each trig substitution. So if our integral contains one of these three things, then the substitution that we're going to make is to the right in the same row. Now, at least for my class, something that I want to emphasize is in my class, most of the time, b equals 1. But I just wanted to show you this more general case. But like I said, in my class, most of the time, not all the time, but most of the time, b will equal 1. And if that's the case, then this is more specifically going to look like a squared minus x squared. And then, as an alternative, we'd get x equals a sine theta. Here, in this next case, we'd have a squared plus x squared underneath the square root. And then that would mean x would equal a tangent of theta. And then here we'll have x squared minus a squared, and then x is going to equal a secant of theta. And a here is just some positive constant. And then we have the corresponding domains, and then in the last column, it tells us which Pythagorean identity we will end up using. Now, if you're worried about remembering these Pythagorean identities, then don't. They can all be derived, assuming you know the three basic ones, which you should by now. So this is the main Pythagorean identity here. I am shortening identity to ID. And then we have secant of theta is equal to 1 over cosine of theta. And then our last identity is tangent of theta is equal to sine of theta over cosine of theta. Let's go ahead and derive the other two Pythagorean identities. So I have sine squared theta plus cosine squared theta is equal to 1. If I divide every single term by sine squared theta, then my first term will simplify to 1. My next term will become cotangent squared, and then my last term will be that is the same thing as cosecant squared theta. And then the other way we could get our third Pythagorean identity is if we take our main Pythagorean identity and divide every term by cosine squared. So sine squared over cosine squared, that gives us tangent squared theta. Cosine squared divided by cosine squared is 1. And then the last thing is secant squared theta. And notice that this corresponds to this identity here. And to get the third one, I can also get that just by subtracting 1 on both sides of this identity. So that corresponds to that one here. So our first example wants us to evaluate the indefinite integral of the square root of 9 minus x squared over x squared dx. And right now I want to take a look at the part that has the square root in it. And if I go back to my table, the square root of 9 minus x squared is of the form a squared minus x squared. And so pause the video if you need to, go back and look at the table that we saw on the previous page. And if we have an integral that contains something of this form, then the trigonometric substitution we use is let x equal a sine theta. But in this case, our a value, since we have 9 represents a squared. So that means that if I take the square root of that, a is going to equal 3. So that's the trig substitution that we're making. That's why this section is called trigonometric substitution. And now we're going to proceed by taking the derivative. So dx d theta is equal to 3 cosine of theta. And then if I solve for dx, if I get my differential, then dx equals 3 cosine theta d theta. So typically for my classes, I am okay with students skipping this step. And so we'll just stick with x equals 3 sine theta and dx equals 3 cosine theta d theta. So now what we want to do is we want to rewrite our original integral. So I'm going to say this integral is equal to the square root of 9 minus 3 times sine of theta squared over 3 sine theta squared. And then dx is getting replaced with what we found here. So 3 times cosine of theta d theta. Okay, so now we want to do some simplification of our integrand. So I have the square root of 9 minus, if I square that thing inside of the parentheses, I get 9 sine squared theta. Same thing in my denominator. Just like we did on the previous page in the more general example, underneath my square root, both terms have a 9, so I can factor that out. And notice underneath my square root, I have one of the forms of the Pythagorean identity. And if you don't remember, go back to the table on the previous page. So that's going to help us rewrite the thing underneath the square root as the square root of 9 times cosine squared theta over 9 times sine squared theta times 3 cosine theta d theta. And the square root, now I can go ahead and actually take the square root of that thing. So that would give me 3 cosine theta. I still have my 9 sine squared theta in my denominator, and then I can move this over to the numerator. I have 3 cosine theta d theta still. Notice that in the numerator I have 3 times 3, and that will cancel with the 9 in the denominator, and then this is going to simplify to equal cosine squared theta over sine squared theta d theta. And that we know from trigonometry that that is equivalent to cotangent squared theta d theta. And in the previous section, we talked about trigonometric integrals. And this is so important as to why we covered that section, because in this section for trigonometric substitution, a lot of the times when we simplify our integrand, it's going to end up being some trigonometric function that we need to integrate, like we have in this scenario. So cotangent squared is not one of those functions that just has a really nice antiderivative. So what we want to do is we want to rewrite this using one of the trig identities that we know. And it just so happens that we derived one of the Pythagorean identities, and from it we can gain that cotangent squared theta from one of our Pythagorean identities is the same thing as cosecant squared theta minus 1. And the reason that we rewrite it like that is cosecant squared has a really nice antiderivative. So I can actually split this up into two separate integrals if I wanted to. And the antiderivative of cosecant squared is negative cotangent of theta. And then the second integral evaluates to theta. So we have negative cotangent of theta minus theta plus our constant of integration. Now, a lot of times students feel like they can stop here and that this represents our final answer. However, remember that our original integral was with respect to x, so our final answer needs to be in terms of x. And the way that we're going to figure out how to change this back into x is we are going to think about the original trigonometric substitution that we did. So from earlier, we let x equal 3 sine of theta. Now, from that, if I solved that equation for sine of theta, we would get that sine of theta is equal to x over 3. And remember back from trigonometry that we had right triangle trigonometry. So sine of theta means that I have some angle theta in a right triangle, and we have SOHCAHTOA. So sine is opposite over hypotenuse, and that means that this represents my opposite side length, and this represents my hypotenuse side length. So here we can fill in x, and then on my hypotenuse I can fill in 3. Now, to fill in the remaining side length, I could use the Pythagorean theorem, and it would tell me that this remaining side length is 9 minus x squared. And that's actually the original thing that we had in our integral, so who knows, is that a coincidence? I think not. Okay, so now from our picture, this is where we can start to gain our values here. So I want to think about what cotangent of theta is equal to. And remember that tangent of theta from SOHCAHTOA is equal to opposite over adjacent. And because cotangent is the reciprocal of tangent, then it should be the adjacent side length over the opposite side length. So that is going to be equal to the adjacent side length, which is the square root of 9 minus x squared, and then the opposite side length is x. So let's go ahead and fill that in here. I have negative square root of 9 minus x squared over x. And now I need to figure out what theta is. And I can do that from this equation here. I know that sine of theta is equal to x over 3, which that implies that theta is equal to sine inverse of x over 3. So coming back over here, I have minus sine inverse of x over 3 plus my constant of integration. So here is our final answer that is now in terms of x.